Hi, my name is Hannah Lohman, and I am a member of the QSDsan group that uses quantitative sustainable design for sanitation and resource recovery systems. In this video, we will cover how to create a waste stream, the major attributes associated with a waste stream, copying, mixing, and splitting waste streams, and composites. To start, we're going to go over the tutorial section and click on the WasteStream tutorial. Before we begin, if you haven't already, you should watch the component tutorial video. If you're up to date on our tutorial videos, you can go ahead and open your Jupyter notebook for this WasteStream tutorial. To start, open a new file wherever you'd like on your Jupyter notebook. I've named this tutorial Tutorial 3 WasteStream. First, let's import QSDsan and check the version we're using. So I already have the code in here, but we can run this cell and we can see that we're using version 0.3.5. And it's okay if you have 3.3 or 3.4. This is just the most up-to-date version right now that we have. And so first we'll go through the first section called creating waste stream. A waste stream object can be created by defining the flow rate of each component, which is similar to the creation of a stream, or through built-in influent characterization models, such as by specifying total volumetric flow rate, concentrations of total COD, TKN, etc., together with COD fractions. And we want to note that QSDsan can work with three main stream classes: the stream, sand stream, and waste stream. Stream is from the package ThermoSteam, while sand stream and waste stream are created in QSDsan. The following tutorial is focused on waste stream as it is one of the core classes of QSDsan. You can learn more about the different classes in the documentation. And so if we click this link, we can see the stream documentation. And so, like I said, QSDsan can work with three main stream classes: stream, which is inside of ThermoSteam, sand stream, and waste stream. And sand stream and waste stream are both within QSDsan. And so this flowchart can help you decide which class is the most appropriate class for you to use. And so we can walk through this as a decision framework. And so first we can ask ourselves if we need wastewater properties for our streams. And if we do need wastewater properties, then we should go ahead and use WasteStream. If we don't need wastewater properties, then we need to determine if we need to be able to conduct a life cycle assessment. And so if we do want to eventually use LCA, then we would want to use SandStream, which is also within QSDsan. And if you don't think you'll ever need to use an LCA, then you can go ahead and use Stream, which is within ThermoSteam. And also in the future, it is likely that the SandStream class will be merged into ThermoSteam, so that LCA can be implemented for systems developed using BioSteam. And so now we will go back to the tutorial and we will start walking through the example code. And so before we get started with WasteStream, we can first check out the documentation of WasteStream. So if we copy this and run the cell, then we can look at the WasteStream. And so every WasteStream that you develop will have the similar attributes. And so the first is every WasteStream will have an ID. And this is something that you can set yourself. But if you don't define what you want the ID to be for the waste stream, then it will be automatically included based on what waste stream you have in the system. And then we can also look at different flows. So something you would want to define is the volumetric flow rate for the waste stream. And then for this waste stream, we're assuming that the phase is liquid. And then there are automatic temperatures and pressures for the waste stream, and then different attributes for each waste stream. And so before we can use WasteStream, we need to tell QSDsan what components we will be working with. And so let's load the default components for this demo purpose. And so we can use components to load the default components for the WasteStream. And then just to remind ourselves what the default components are, we can go ahead and see what the compiled components are. And so these are all the components that we have included that you can use for your WasteStream. And so a lot of these are typical things that you would be interested in related to wastewater. And so these are the components that you can work with when you're using your WasteStream. Okay, so now we will move on and define the component flow rate. And so you can initialize a WasteStream by setting the flow rate of the component within it. And typically we use lowercase when we're naming the ID of the WasteStreams. So that's just a convention that you can keep in mind when you're creating your own WasteStreams. And so we can start with the first WasteStream. Let's call it WasteStream 1. And so here we have the WasteStream ID. And so, like I said, it will have an automatic ID if you don't put anything in here, but it's easier to keep track if you name your WasteStream the same as the variable that you're calling it. And so here we have it called WasteStream 1. And then you can add values for different components you want, and also identify what unit these values are that you're importing. And so here we've added values for two different components, and then both are in terms of kilogram per hour. And so if we want to look at this WasteStream, we can go ahead and show it. And so here we have our first WasteStream. So we have called it WasteStream 1, so you can see the ID right here. And it's liquid phase, temperature and pressure are standard. And then here you can see that we have identified two component flow rates in the system. And so notice that the automatic unit is grams per hour, and we inputted kilograms per hour, so it automatically converted these values to be in grams per hour. And then, yes, so you can use different units in defining and also showing the stream. And so we can go ahead and try this out. Let me just add some more rows. Okay, so I'll copy this code in. And so here we are looking at WasteStream 1 again, but we are going to change the inputs to be in kilomoles per hour. And so, yeah, we are importing in kilomoles per hour for these components, but then we want to show it in kilograms per hour. And so it will do the automatic conversion for us. Okay, so here now we can see for the flows, for the two values we inputted, we brought them in using kilograms per hour. And so now we can see it in kilograms per hour, or we brought them in kilomoles per hour, but then now they are in kilograms per hour when we're seeing them. And then also we have changed it where we want to see the concentrations in grams per liter instead of milligrams per liter. So we can see that that has also updated for us. Okay, so moving on, you can also get other information such as total dissolved solids, volatile, suspended solids. And so you can use different code to see that. And so here we can see what the volatile suspended solids are. And so you can see that it is this value. And so you can use this with TDS and other components that you're interested in looking at. And to learn more about the attribute for example, if you're interested in what the unit was of the volatile suspended solids, you can check out the documentation using the question mark. So now we'll move on to section 1.2, where we are going to specify component concentration. And so we were just dealing with flow rates, but sometimes in some situations, you might prefer concentration over flow rates. And like I've mentioned before, if you don't provide an ID for your waste stream, then QSDsan will automatically assign a default one. In terms of WSX, where X will be a number and it'll always start with 1 and then increase in value as you're creating more waste streams. And so now I will add in this code where we can look at concentration instead of flow rates. And so here we have defined our waste stream as WS2, and then now we're going to set the flow by concentration. And so we're saying that the total flow rate will be 100 for the system, and then for the waste stream, and then the concentration. So we're going to set calcium to be 100. And here you can define the units. So this first unit is referenced to the flow rate. So we have 100 liters per hour. And the second unit is referring to this concentration. So the concentration of calcium will be 100 milligrams per liter. And so now we can look at this waste stream that we just defined and see what it looks like. And so here we can see the ID is now waste stream 2, and we didn't specify the ID. We just let QSDsan create the automatic ID for this waste stream. And so since we already had waste stream 1 above, then the next waste stream would be waste stream 2. And so now we can look at the flows in terms of grams per hour. And so we can see that the calcium is in here. It did the conversion to put it into grams per hour. And then component concentrations, we can see that our values are in milligrams per liter, and we have our calcium down there. And so now we'll move on to using wastewater models. So now we have figured out how to create a waste stream, and now we can use the specific waste stream models that we have developed within QSDsan. Okay, so before we get into the models, we can, well, first I'll say that there are 4 influent characterization models that we have developed in QSDsan. And for example, the one that we'll be going over is COD states. And so this model is COD states influent model. And so first we'll look at the documentation for COD states. So I'll pull this up so we can see it better. So COD states has similar arguments for the waste stream. So the first argument is the same. We have the ID, and right now it's empty because that's something that you would want to define when you're using this model. And then if you don't identify the ID, then it will be automatically assigned. The second argument is the total volumetric flow rate. And so it starts off as 0, and this is also something that you would want to define when you're using this model. And so this function is written assuming that the stream is liquid. So you can see that the phase is L, which is liquid. And because it's assuming that it's liquid, you wouldn't want to use this model if you're not looking at a liquid stream. So you would want to consider other models if you're dealing with a stream that is not liquid. And so you can specify wastewater related arguments. For example, you can specify what the COD is, the TKN, TP. You can specify a lot of things to make it representative of the stream that you're interested in. But the simplest way to use this model is to just set the flow rate to something other than 0 and give it an ID. Okay, so now we can use this model. So I will copy this code in here. Okay, so this is the model example that we're looking at. So we've identified the ID as WasteStream 3, and we have also identified a flow rate. So those are two important things that you should define when you're using this model. So we have the ID, we have the flow rate, and then we've also added different other things such as pH, COD, and TP. And so if we want to look at this model or this waste stream that we've defined, we can go in and see that the ID is WasteStream 3 that we defined, and the flow rate is 1000 total flow. And then you can look at the pH that we've defined as 6.8. The COD, if we scroll down, is 100 milligrams per liter. Total phosphorus is 11 milligrams per liter. And so, yeah, that's an example of how you can set up a waste stream using this model. And I will say that, so each model has different assumptions about the ratios of components, and they have different arguments as well. And so some models might be more typical for using with sludge as an example, and some might be better for using with municipal wastewater. So you'll want to figure out what model makes the most sense for you when you're defining your own waste streams. Okay, so now we'll move on to the next part, which is looking at the major attributes of your waste stream. And so first, the first section is retrieving the flow information. And so in many cases, we'll want to get the flow rates of all components at the same time. And to do that, we can use this code using .fmass. And so that will help you, that will allow you to get the total flow rate of the system. So I will copy this code in here. And so here you can see we used .fmass, and that allowed us to get the total mass flow rate. And so the total mass flow rate of WasteStream 3 is 982.4 kilograms per hour. But you also might just want to know what the flow rate is for a specific component. And so here, if we're interested in what the flow rate is of just the water component, you can see that it is 981.47 kilograms per hour. And so .imass is used when you're identifying a specific component that you're interested in, but if you want to know the total flow rate, then you would use .f_mass. If you want to look at everything, you can just use .mass, and it will give you the entire array. So here you can see the water that we identified was 981.47. That matches to what we were looking at here. And if we were to add everything up in the entire array, then it would be this 982.4, which is the total. And so similarly, we can also do that with molar and volumetric flow rates. And so first, if we look at the molar, let me add in some more lines. Okay, so we can look at the total flow rate. We can look at, or the total molar flow rate. We can look at the molar flow rate specifically for water, and then we can look at the entire array. And so here the total molar flow rate is 55.1 kilomoles per hour. Specifically for water, it is 54.47, and then here we can see the entire array. So all of these units are in kilomole per hour. And then similarly, if we just want to look at the volumetric flow rate, same idea, .f mole is, or .f VOL is the volumetric flow rate. IVOL is if you're looking at a specific component, and .VOL is if you want to look at the entire array. So here we can see everything is pretty similar to the examples above. And yeah, you can also look at concentrations with .conc, .concentration. And you can see the entire array of all of the components, the concentrations of each. And this is in grams per meter cubed. And you can update arrays as you like. And so here I will copy this code to show how we can update arrays. And so first, we'll just print what it was before updating. So the mass flow rate of water is just whatever the waste stream was, the mass flow rate of the water component. And you can update it. So let's say we want to double the mass flow rate of water. So you can use this equation. So ws3.imass, identify the water component, multiply equals to 2. So that's just saying multiply it by 2. And after updating, we can see what it will look like. So here, first it was in the 900s, and then we had that equation where we're multiplying by 2, and you can see that after updating, we're able to double it. So everything looks good right there. And similarly, you can also divide it by 2. And so here, this line is printing the value of what it was before we updated. And then here we're dividing it by 2. And then here we're printing what the new value is. Oh, and we were also, instead of just doing the water array or the water component, you can do it on the entire array. So here we weren't just doing the water, we were doing the entire array. So here we can divide the entire array by 2. So if we go down to the water component, we can see that it used to be 1962 when we redefined what that was, and it has now divided by 2. And every other component in this array, each value has also divided by 2. So it's a really easy way to update the entire array if you need to double it or do the same multiplier across the board to everything in the waste stream. And so now we'll move on to discussing copying, mixing, and splitting for different streams. And so this is really important when you're now combining streams. If you're wanting to model a specific wastewater treatment plant, we won't just have one stream, we'll be having splitting of streams to different treatment processes. We'll have things combining. And so these are really great for when you're actually getting into the more modeling of your wastewater treatment plant. And so first we will copy. And so copying is really simple. You would use it if you have a waste stream that is already existing and you want your new waste stream to be an exact replica copy of that waste stream. And so we can just use .copy to make the new copy. And so here we want to copy waste stream 1, and our new waste stream, which is a copy of waste stream 1, will be called waste stream 4. And we, instead of letting QSDsan create its own ID for this waste stream, here we're going to name it copy of waste stream 1. And so now I will show you what it looks like. So here we have an ID, and it is the ID that we identified, copy of waste stream 1, and everything else should be an exact copy of waste stream 1. And we can also mix 2 streams. You can actually mix many streams, but for this example, it'll just be 2. And so that's you have 2 streams and you want them to come together to be 1 stream. And so I will copy this code over. So first we want to define waste stream 5 as a waste stream. So you need to do this first. So so QSDsan knows that WS5 is a waste stream. And once you have waste stream 5 defined as a waste stream, then you can mix two streams together to form WasteStream 5. And so here we want to mix WasteStream 2 and WasteStream 3 together to form WasteStream 5 using .mix_from. And so once we have that code, we can run it and see that we have this new waste stream. Oh, I guess we didn't define the ID for the WasteStream 5, so that's why it says WasteStream 4. That's the automatic ID that QSDsan gave it. And so everything you would see down here is a mix of WasteStream 2 and WasteStream 3 to form this new waste stream. So another example is if you have one stream and you want to split it into two streams. And so this code is an example of what that would look like. And so first we need to define the waste streams that we want to split a stream into. So waste stream 6 and 7, we are defining those variables as waste stream variables for both of them. And so once we have our waste stream set up for the split, then we can split waste stream 5 into these two. And so here we have the two waste streams that we are splitting, waste stream 6, or these are the two waste streams that the stream is splitting into. So we're splitting waste stream 5 into waste stream 6 and waste stream 7. And the split is defining how we want waste stream 5 to split. And so 0.3 of the stream will go into waste stream 6, and 0.7 of waste stream 5 will go into waste stream 7. Oh, sorry, we didn't print anything. So we have that new waste stream, and here we can print this line. So we're going to print the mass flow rate of waste stream 5, the mass flow rate of waste stream 6, the mass flow rate of waste stream 7, and then we can look at the difference. So let's see what happens. So our initial waste stream mass flow rate was a little over 1,000, and we split it. So when we split it, we said we wanted a third of waste stream 5 to go into 6 or 0.3, and 0.7 we wanted to go into waste stream 7. And so here you can see that waste stream 6 has the mass flow rate of waste stream 5 times 0.3. So the fraction looks like it worked out. And we can also take the difference if you really want to check to make sure everything is okay with your waste stream split. And so here we did the mass flow rate of 5, subtracting out the mass flow rate of 6 and 7. So realistically, this should be 0 or really, really close to 0, because 6 and 7 should be 6 plus 7 should equal 5. And so here this number is practically 0 with the exponent to the negative 13. So the split works correctly, and you can use this if you want to check to make sure that your flow rates are correct and you put the right value into split. And so another thing with splitting is that you can set the split for each component. And so in this example, we were saying split everything, every component in the waste stream with this value. But what if you have a different split value for different components? So you can identify the split for each specific component. So in this code, we are identifying waste stream 8. And so we're defining the values for these components in kilograms per hour. And it looks like we want to split waste stream 8 into waste stream 9 and waste stream 10. And so these are the components in waste stream 8, and we can define different splits for each component. So the first component, we are saying we want the flow rate of this to be split 50-50 between the two streams that we're splitting into. But for water, we want it to split 0.8 into the first stream and 0.2 into the second stream. Okay, so now I can show this new, we'll just look at WasteStream 9. So the first stream that we split into. So here we can see that for the flow in kilograms per hour. So this was 1, and we said we were going to split it 50-50, so it should be now 0.5 kilograms per hour. This one was 1,000, and we said we wanted the first stream to get 0.8 of the 1,000, so that's here we can see that it is 800 kilograms per hour. So the split, we were able to successfully split these using different values for split. And now if we look at WasteStream 10, the second stream that we created with the split, you can see since this was 50-50, this first value matches that because they both received equal amounts, but then this stream only received 20% of the original stream for water, and so that is why this is 200. So it was 200 out of the original 1,000. Okay, so now we'll move on to composites, where we can talk about the different composites of the waste streams. And so the composite method refers to commonly used composite variables in wastewater treatment modeling, and we have a lot of composite variables that have already been stored as attributes of the waste stream. And so, for example, some common composites to wastewater treatment modeling, we have COD. That is a very common composite that we would be interested in. And so you can see that it is an attribute that works for this waste stream. And so the value for COD for this specific waste stream is 251. And you can also just in the comments, so you can try this with other composites such as total organic carbon, TKN, TP, THOD. So you can try it with a lot of different composite variables. And just as a note, so for the composite variables related to dissolved or suspended solids, they are available as methods. Methods are function specific for the WasteStream class, because in the wastewater community, there is a little bit of a controversy around whether the colloidal components should be considered suspended or dissolved solids. And so we didn't want to make this decision for you when we were developing QSDsan waste streams. And so you can decide for yourself if you want to consider colloidal components as dissolved solids or suspended solids. And the default is to not include colloids. So this code, we can show how this works. So I will go ahead and run it. So the first line of code is assuming that it is without colloidals in the volatile suspended solids. And so here you can see your line of code is the WasteStream.get VSS. And if you do want to include the colloids in the volatile suspended solids, you will just add this into your code, include underscore colloidal equals true. So that's saying, yes, include the colloidal, the colloids in the volatile suspended solids number. And so here you can see without colloidals, the value is 92.0. And then when we did indicate yes, go ahead and include the colloidals in the volatile suspended solids, the number increased because we were including them to 110.6. And so this obviously wouldn't matter if your waste stream does not have colloidal components. And so I can use this code to show that it doesn't matter which way you go if you're not even dealing with colloidals. And so here we're looking at WasteStream 1. And so it's the exact same line of code that we used previously, just we're switching out WasteStream 3 to WasteStream 1. And you can see that both numbers are identical, and that's because WasteStream 1 doesn't have any colloidals to include. So even though we said, yes, go ahead and include them, there was nothing to include. So that's why the numbers are the same. Okay, so the composite variables above, COD, VSS, TKN, all of those are calculated using the composite method. And you can calculate all kinds of composite variables by specifying the different arguments for this method. So you can look at the documentation for the WasteStream composite on your own time, and you can figure out specifically what that looks like. And so for this example, we want to calculate particulate BOD of the WasteStream object. So we just need to specify the composite variable as BOD and the particulate size as X. And so here we want to calculate particulate BOD. And so we were using the composite method. So vs3.composite, we're specifying we want to calculate particulate BOD and the particle size is X. And so we were able to calculate what that value is. And these are more examples of different composite variables that you can calculate. And so you can calculate the biomass COD. So looking at the composite variable of COD, specifying that you want to look at X BIO, biomass. You can calculate nitrogen as nitrate, nitrite. So here we have included nitrogen or nitrate and nitrite together as NOx. And so the composite variable would be N for nitrate, nitrogen, and then the specification is S_NOx. And you can do the same with, if you want to look at the total organic carbon, the composite variable is carbon C, and here you would specify organic equals true. So if you look at the documentation for .composite, you'll be able to see everything you need to know about successfully calculating the composite variables. So I can just pull it up for you now. And so here you can see these are the different inputs that you can use. So you can specify that you want it to be organic. You can specify, so here, let's start with the variables. So these are the different composite variables that you can consider. So most of them are common to wastewater treatment, different composite variables that you would be interested in. So you can look at COD, BOD5, different nutrients, carbon or nitrogen, phosphorus, potassium. You can look at the solids, the charge, although we're still working on the charge right now, so I wouldn't use charge right now. And then, so the subgroup, you can look at the compiled components. The default is none. Particle size, so these are the different things you can put for particle size. So X, what we're using before, stands for particulate. Degradability, if you want to look at something that is undegradable, slowly biodegradable. If it's organic or inorganic, organic will be true, inorganic is false. And then, yeah, specification, you can use one of these, the default is none. So definitely go through and look at this if you're looking at how to calculate a specific composite variable that you're interested in. Okay, so this is the end of the WasteStream tutorial video. I hope that you found it really helpful and are able to successfully feel confident about using the WasteStream within QSDsan. And I would really take advantage of going through these tutorials and getting more familiar with the documentation in QSDsan. And our next tutorial will go over SAN units.